So I'm going to kind of walk you through what this looks like. So again, you're given this, you're given these, and you're supposed to find equilibrium concentrations. So you are going to, or we are going to actually down here along our changes, we're going to strategically come up with a value x. It's a variable. We're just going to say the change is x. And then relative to stoichiometry, we can find the other x's once we assign this x. Okay, well, it's easier to show you, but that's kind of general what we do. So we're going to assign the x, assign the changes for everything in terms of that x. Okay, then what we can do is kind of like what you guys did for your homework. In order to get the equilibrium, basically we take the initial, apply the change, and come up with the equilibrium concentrations. I definitely will take your homework whenever you're ready. So didn't want you to think that, okay. So it's kind of simpler. We're going to use ice charts. Okay. So I know it's kind of weird, but what's going to happen, and you probably can kind of, if you're following along, you'll basically get this quantity down here, and it will be something minus x or something plus x. You're going to get an x variable here because you took this and you applied your change. So you're going to get some terms down here that look icky. Sorry. We can apply, just like you did before, we can plug these back into our KC expression. Now remember, we have this value. We have this value. And then you're going to have some x minus blah, blah, x minus, I guess it would be like, 3 minus x, 2.5 plus x. You're going to have something that looks a little icky there. And I'll try to show you in the example, but on your test, that is where you get to stop. On your test, that's where you get to stop. We're going to take these other, though, we're going to use the quadratic equation, which some people love. I don't know why you love the quadratic equation. Okay. And I'm going to show you online where you can find the quadratic equation thing. And if you want to, for your homework, use the online tool. I'm cool with that. Because some people have it on their calculator. They can solve for x. So bottom line is if we have a number here, because we're given KC, and we have one variable here, which is x, we can actually solve for x. Then the beauty is, once we have x, okay, then the last thing is we're going to take that x, we're going to plug it back in here, and we are going to get the real numbers. So remember we had, this was initial, apply, change. So we're going to take initial, and now we have a value for x. We can really get those values. So that's kind of what we're going to do. All right. And before I forget, because sometimes I do, oh my gosh, I really do. Do you see where this is one of those problems you can check? Here's the deal. Okay. So once you get all of these, okay, because you have a value for x, you got equilibrium concentrations, you can plug them back in to your expression and see if you get the KC which you were given. So it's one that you can check, good, bad, or otherwise you're like, oh, it didn't work out. But okay, so here we go. We're going to work two examples, and I think I'm going to kind of erase that. And put them on this board for the first one and maybe that board for the second one. So let me go ahead and jot this down. We have H2, 1 mole, right, reacting with 1 mole of F2 in their gaseous state to form 2 moles of HF. I'll go ahead and put this whole thing up here. So, we've been talking about how we can take that equilibrium and write an equilibrium constant expression. Let's go ahead and do that. Erase this. So our KC expression for this one, it's always products in the numerator. So we put HF, molar concentration, squared, divided by the molar concentration of H2 times the molar concentration of F2. Be careful, if it's a solid, it doesn't show up in your equilibrium constant expression. Okay, and we are given the value of KC, 115. All right. So the other thing it says is that initially Initially, we have these moles here. We have, I'm going to put them, let's see, let me go ahead and say this is the molar concentration of H2, this column. This column is going to be the molar concentration of F2, the two reactants. And then this column is going to be the molar concentration of HF. Okay? And I'm going to, in parentheses, well, I'll just go ahead and do it this way. If you read it a few times, notice that we have 2.00 moles of H2 running around in 2.00 liters. Don't forget that we need molarity. So we're going to get molarity that way. And we have 4.00 moles of F2 running around, again, in the same common container, 2 liters. And notice this is one of those where it doesn't say anything about the HF. And if you read it a few times and you still don't find any HF, there's none. So what we're supposed to do is come up with these values down here. So here we go. Oops, you guys probably don't need that, or did you need that? Sometimes working chemistry problems, even if we didn't need the equilibrium constant expression, it's just helpful to go ahead and write it down. You're like, oh, well, that's something I may or may not need. And as it turns out, of course, you probably figure out we'll need that. So we need to knock out the molarities. So actually, then this molarity is what, 1.00 molar, and this molarity is 2.00 molar. Not very good. And none with the HF. So looking at it, do you see where, if we go ahead, and like I think it says right here, if we go ahead and pick on our H2, of course we have 1 mole reacting with 1 mole to form 2 moles. Okay, 1 mole of each. If we just go ahead and make this change a negative X, do you see where it's an equal molar concentration with the F2? So that's going to make this a negative X. And that's actually going to make this a plus 2X. I'm over here in my product column. Does that make sense? Cool. And why did we do that? Well, I'm trying to think. The suggestion is always to pick something that is just in 1 mole amount and set that equal to your X, and then everything else kind of falls into place. Cool. Well, then what I said was we go ahead and take our initial and apply our change. So the first column is going to look like this. At equilibrium for the H2, we're going to have 1.00 minus X. For the F2, 2.00 minus X. And for the HF, I'm getting 2X. Because it's 0 plus 2X. Does it work?
I was confused about the 2, but I got it.
Yeah, my columns are getting kind of messy here. Okay. That's what this slide says. I don't know what you guys need to fill in. I do like the ice table. And then what we need to do, and I warned you it will look ugly, we can basically take this pattern and substitute in these equilibrium concentrations with the X. So be careful. It is a very common mistake. Notice I have HF squared, a very common mistake. Here's my HF equilibrium concentration, 2X, very, very, very common, squared. And then in the bottom, we have the equilibrium concentration of H2, which is 1.00 minus X, times, and that's raised to the first power, times the molar concentration of F2, 2.00 minus X. And that, again, is equal to 115. So now in my notes I say kind of, I introduce the idea of the ice table, but I still like the ice table and the other one too. then this looks a little different because it's missing that line, that kind of between the change and the equilibrium. So we said we basically take the initial, apply the change, and come up with equilibrium concentrations. All right, so far so good. So, believe it or not, and I've kind of debated how I want to do this. I think I know how I want to do this. We now have one equation and one variable, and we can massage this and get to x. But a minute ago, did I put exam or stop or something? Okay. This actually is how far you need to get for your exam. This is what you need to be able to set it up for your exam. Well, I'm going to take it all the way and solve for x. I think you have homework to do that too. I guess this would say in your homework, if you get this far, I'm cool with that. I'm going to show you how to solve for x using the quadratic. All right. So in order to solve for x, we need to flatten that thing out. So I'm going to kind of create a little, I'm going to create a whiteboard here. Okay, and I'm going to show you in my humbleness how I would teach somebody to do this. So here we go. And I will go ahead and I'll take a snapshot of this and push it out there. So basically, we are solving for x when we have Kc is equal to, let me make that smaller, equal to quantity 2x squared divided by 1.00 minus x times 1.00, excuse me, times 2.00 minus x. Okay, so my idea is equal to 115. My idea of flattening it out is basically, and I think I might have said this before, I kind of assume that 115 over 1, and then I kind of cross multiply. That's just how I do. So then I end up with 115 times 1.0 minus x times 2.00 minus x is equal to 1 times quantity 2x quantity squared. So I flattened it out. Now I'm going to solve for x. So now here's where what I learned it. I'm actually going to take these two polynomials. Are they polynomials? I don't know. I'm going to take those two terms and I'm going to go ahead and I'm going to fix it. Yeah. Padiddle them. So I'm going to keep my 115 along for the ride, and I'm going to take that now. It's like that smiley face, if you guys learned it. Basically, what's that? Yeah, the FOIL. And make sure I do this right, guys. So I would take the 1 times the 2, and I get, without the x, 2.00. Okay? And then I would take the negative x times 2 and negative x times 1, and to me I get 3.00x minus 3.00x. You buy that? I do. And then the last thing I need to do is to look at my x terms. Negative x times negative x, of course, is positive x squared. Okay? So if we're okay with that, something like that. And then I'm going to go ahead and clean up my quantity 2x raised to the second power. So don't forget that squared needs to apply to everything. So basically, of course, 2 squared is 4, and x squared is x squared. So I actually get 4x squared there. I brought along my calculator just so I could not butcher this entirely. And so now I'm going to take that 115 through. Okay, so if I take 115 times each one of these terms, Then I end up with 115 times 2 is 330, right? 330 minus 115 times 3, 345x plus 115x squared. Does that look okay to everybody? Me too. Is still equal to 4x squared. I'm getting close. So I'm trying to think, the standard form, I'm trying to get to a plus bx plus cx squared, aren't I? I think so, is equal to 0.
Mm-hmm.
Okay, good. Awesome.
So you have
Okay.
to subtract the 4x squared.
Yep, so now I need to, yep, I'm getting close. Yep, like Morgan said, if I go ahead and subtract 4x squared from both sides, then I'm close to standard form. So 330 minus 345x is plus, now if I knock that down 4 units, I got 111x squared is equal to 0. We okay with that? Okay, so that is standard form. So the way that works is when you plug it into, if you're using that little app on the internet or if you're using the quadratic formula, this value is A, this value, negative 345, is B, this value, 111, is C. Did I do that wrong? I did it backwards. Oh, okay, that's close. So this value is A, thank you. The middle value is right. The value for B is still negative 345, and the value for C, thank you, is a positive 330. Final answer. Yay. Okay, so that's how I flatten it out, and that's how I got the values, the variables. And again, you don't have to do it on a test. I do have you doing it on homework, but if you don't do it on homework, I think I could live with that too. Okay. So, is that what I had? Okay, good. Okay. All right.
I thought it was 330. Yeah, 330.
Oh, yeah, so I must have, let me see. I'm going to pull that up again.
Oh, it is 230. It was 230. Yeah.
I did have 230? Okay.
Well, you said 330, but
I really meant 230. Okay, good. Wonder, is this where I put it? I just kill it. Well, I can't find my work now. Yeah, I'll have to take your word for it. Okay. Maybe this is it. No. Okay. Okay, so we're all on the same page now, it sounds like. Okay, good. See, I had a mistake. So that up there in the corner is where you're going to plug in your A, B's, and C's, but I would suggest you not worry about it. I hate the quadratic. Some people love it. Your calculators, I think mine does, it actually has a way to use it to plug in A, B, and C. But if you plug in A, B, and C, this is what it looks like into the quadratic. Now, the thing about the quadratic equation, I don't know if you remember this, but actually you end up getting 2 solutions. And the reason you get 2 solutions is right here. This is why you get 2 solutions. Because you are adding the square root of a quantity, and you're also subtracting the square root of a quantity. So you end up with 2 solutions. But in problems like this, one will make sense and one will not. So I'm just have to take my word for it that if you plug in, actually you will come up with two solutions. Now, this actually I pushed out on Twitter, this website I'm going to show you. It's just one of many. This is that online thing that I told you about that I would use for my homework if I was you. And do you see where it has a place for you to put A, B, and C?
That's awesome.
I know.
So cool.
Okay, so yeah, so that's under Twitter right now. But you could find them anywhere. And then these are the 2 solutions it's going to give you.
And next one is positive, and next 2 is the negative when you subtract.
It depends, not necessarily, but I'm going to show you that even if it's not, when you plug the x value back into where it is on your ice chart, one will make sense and one will not. but I don't think they necessarily have one positive and one negative.
Yeah, it just depends on
Yeah, I think it does. So, yeah.
No, I meant like in this equation, when it's plus or minus, like, so, is that like the x1 result would be the?
Yeah, but I still
okay.
think, I still think that, you won't, it depends on the magnitude of your variables.
Okay.
I'm not, I don't know.
I remember working problems where both of them were negative and both were positive.
Yeah. So it kind of depends. And that makes sense. Like, for instance, if your B is very big, you could actually end up with, I don't know, 2 positives. Or wait a minute, that B is negative. I don't know. I hate the quadratic equation. But you can. Maybe. So, do you want to plug it in? Do you want to see how it works? Sure. So you guys got to remind me. Tell me what's A is.
111.
111. Oops. Why did I put 110? What's B?
Negative 345.
Negative 305?
45.
Negative 45.
No, 345.
Thank you.
Sorry.
Awesome. And C?
230.
Solve. Dun, 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 dun. Okay. So I'll go ahead and show you while those are up here. I know it's kind of small. I'll make it a little bigger. I'll go ahead and show you. Like if you plug they're both positive. If you plug 2.1 in here, does that make sense? You're literally going to take that x and you're going to put it here. 1.00 minus 2. You're like, dude, you can't do that because you only started out with 1. And it's a physical quantity. So here in a minute on my slides, I'm going to say that one goes away. You won't be left with very much. But if we go with 0.9684, yeah. You're not going to have very much at equilibrium, but you'll have a smidgen of H2 left. So one will make sense and one will not. Yeah. Okay, so that's kind of the way that works. You buy it? I do. Now for our second example, I'm not going to, pull myself through flattening it out and getting the wrong A, B, and C, and plug it in quadratic. But my notes will go ahead and show you that. Okay. All right. So now what you're going to see in the notes, we're almost done. Okay, now we're ready to basically just do a little subtraction problem to get the equilibrium concentrations of everything. Over here, we just have to take what? That 0.968 times 2 to get the equilibrium concentration. And then, like I said, we can check, this is so exciting, you can check your case, you can check your work by plugging back in and seeing if you get 115. That's it. So if you take 1.00 minus 0.968, you get, and remember since we're subtracting, we have to round according to decimals, and we're only allowed 2 decimals according to the molarity. So that's why you see the 0.03. If we take 2, subtract x, then we get 1.03 moles per liter. And if we take 2 times x, now in that last thing where we're multiplying, we round according to significant figures, and we have, oh, well, I guess 2 is an exact number, so maybe you don't, you're allowed, I guess I'll go with that. You're back to kind of 3 decimals. But 1.936 moles per liter of our product at equilibrium. So these are equilibrium concentrations.
Wouldn't it just be 1.94 if it was just 3?
Yeah, but the 2 is exact because the 2 actually came from stoichiometry. And then the way I think of it is you're back to basically taking this number and adding it to itself. And then you're back to decimals, which is 3.
Okay, so it's just like the molar masses then.
Mm-hmm.
Okay.
Yeah. But if you gave it 3 sig figs, I'd be fine with that. So, but really, are we okay? Let's do another one. But you know this one has to be a little harder. Because this one, I'll go ahead and start putting it over here. Well, can I take a picture of this and then, okay, that'd be easier. Raised to the first power, all divided by the molar concentration of COBr2. And our Kc is given, and it is 0.190. 0.190. Notice that, and I'm going to wait for the next slide. I'll go ahead and make my columns. So in the first column, let's go ahead and put the molar concentration of COBr2. In the second column, the molar concentration of CO. In the last column, the molar concentration of the other product, Br2. So basically, in this case, they are giving us their masses and volumes. So we have to take those masses and volume, single volume. Take those masses, convert them to moles, and then divide by the volume. Okay. So, but what I started to say is this one's a little bit different because we have a little bit of everything. Notice we have each of the products and we have the reactant. So we kind of looked at this before. It's like the first question is what direction will the reaction go to get to equilibrium? Because you need to know, you know, the stoichiometry is awesome. So we could go x, okay, minus x, but that's assume that it's going that way from product to reactant, from products to reactant. Or we could go minus x plus x plus x. That's assuming it's going this way, okay? You need to know which way it's going to go. So actually, kind of on the front end, we're going to have to come up with a reaction quotient, bottom line. So here we go. Okay. So here's the equilibrium constant expression. Kc is equal to the molar concentration of each of the products raised to the first power because their stoichiometric coefficients are 1, divided by the molar concentration of the reactant, also raised to the first power. The reaction quotient, the snapshot of what the initial conditions are, is the same relationship, okay? And one of the things, and all my notes don't do this, but I've done it before, the distinction between these two expressions, that's the word I was after, it's the same expression, is that these are at equilibrium. I could put a little e here next to the molar concentration of all these things. These are at equilibrium. And these are all initial. I don't know if you want to put a 0 initial, in our case, okay? That's how they're different. So we've done problems like this before. Either way, for the whole working the entire problem, we need to come up with molar concentration. So here we go. The initial molar concentration of the CO, considering the mass is 33.4 grams divided by the volume, 1.50 liters. And then if we introduce the second term, which is the molar mass of CO, 1 mole over 28.01 grams, notice units of grams cancel. We're left with moles per liter, which is perfect. So 3 sig figs, we can go ahead and jot that in now, our ice table. So that's the initial concentration of the CO. 0.795 moles per liter. For the Br2, we'll do a similar thing. Its mass was 70.7 grams divided by the volume, 1.50 liters, times the flipped version of its molar mass, which is 1 mole over 159.80 grams. Again, grams will cancel. We're left with moles per liter. For Br2, rounding to 3 significant figures, its initial molar concentration is, I guess this will work. I'm going to move this guy over. Its initial molar concentration is 0.295 moles per liter. And then last but not least, the mass of the reactant was 128 grams divided by the volume, which is 1.50 liters, and then introduce its molar mass, the flipped version of the molar mass, 1 mole over 187.81 grams. It's molar mass. Grams will cancel. We have moles per liter of COBr2. Again, rounded to 3 significant figures. Its initial concentration is 0.454 moles per liter. So we're not ready to do our ice chart, really. We need to find out which of these 2 scenarios it is. Okay? Is it going to be forming reactant, or is it going to be forming product? And to do that, we actually come up with a reaction quotient.
I was gonna ask, do you just plug those numbers into the QC and then you just compare it to the?
Exactly. Just plug it into the QC and then compare that value to the 0.190. Exactly. So these are the initial concentrations of the reactant and the 2 products. So those are just these up here. And they're all stoichiometric coefficients of 1, which is nice. So raised to the first power. And we said, and I always have to think through this, so sometimes I get it wrong. Like I didn't tell you guys, but the whole orange-yellow thing I got wrong yesterday. So chromate is yellow and dichromate is orange. I should have known that because I've done experiments with those 2. So anyway, I fixed it and pushed it out. But on the video, it's still captured. So we said that you compare that, like you said, to this, and it looks a little bit larger. So if your QC is larger than your KC, then you have too much product. All right? So if you have too much product, then I'm like in scenario number 1. You have too much product. So now we know what to do. So the product needs to go to form reactants. And it does so by subtracting. So this is no. No. Whoa, no. Okay? So again, you know, we do the whole X thing. What do you think, Marie?
Oh, no, that's fine.
Okay. The stoichiometry is wonderful, you know, so we don't, everything's X's across the board, but you need to know which direction it's going. Okay. So now we know the drill. We can come up with these equilibrium concentrations. They look like this. Basically, it's initial, apply the change. So for the first one, it's 0.454, apply the change, which is plus X. To the second one, or to the first product, I guess I should say, it's 0.7, second column, 95, apply the change, which is minus X. And for the last column, it's 0.295, also minus X. So you know what we did before, we got to do it again. Basically take these quantities, these 3 quantities, and plug them back into our expression. And this is where I told you before, you can stop right there. So this is the ice table in my notes. So notice that it's like, oh my gosh. See, this is my first column, and this was my second, and this is my third. But it's the same diff. I know, it's like, what? So, okay. So there's our equilibrium constant expression, and here it is substituted. And it looks icky, but you can totally stop here. On a test, I'll try to explain what I mean stop here. I think I did describe it something about get to the point where you have one equation with one unknown. So that's our one equation with one unknown. You can definitely stop there. These are even worse numbers than we had before. So I'm not going to kind of belabor flattening it out. But if you get it in standard form, which is ax squared plus bx plus C is equal to 0. Then you can take those A, B, and C and plug them in your quadratic. So here's what it looks like in standard form. Believe it or not, you end up with A is 1. A is 1. B is negative 1.280. And C is 0.148. So A is equal to 1. This is B. And C is this. Okay. So for your homework, in order to kind of finish it, you're going to need to do however you want to do it. Like I said, I do it online. Plug it in. And when you plug it in, you're going to get 2 solutions. And one of your solutions will not make sense. So your 2 solutions are 1.15 and 0.129. So I go back down here. So I'm like, the first one does not make sense, does it? 1.15. But the second one looks fine. 0.129. 0.129. 0.129. And we're almost done. So now on the next slide, what you're going to see is basically all 3 of these x's are substituted out for 0.129. And we come up with real equilibrium concentrations. So I'll just put all these up here. So when you substitute in the x for the CO, these are kind of backwards, aren't they? I'm going to go over here to my middle column. When you substitute in the value, the 0.129 value for x, you end up with 0.666 moles per liter is your CO. For your BR2, 0.295 minus 0.129 is 0.166 moles per liter. And then over here, for your reactant, if you take 0.454 plus 0.129, you get an equilibrium concentration of 0.583 moles per liter. And again, this is where you could take these 3 values, plug it up here, and do a quick check to see if you get the Kc value, which you may or may not want to know. Okay, so let's take a look at what's going to be due on Monday. They look like this. The first one? Yeah. Okay, so got the ice table, got your equilibrium, write your equilibrium constant expression. Notice it's always a little bit different. In this case, you are given the moles of H2 and I2, and notice that you don't have any product. That's fine. So this one, notice the change. We didn't have to do any Kc calculation because we know it's going to go that way. So I have minus x plus 2x. Again, then we can, those red boxes you can get by just a calculation from moles divided by volume. So we can get the green there. Those will be our statements in terms of x. And we can substitute back in here just like we've been doing. Notice the Kc was given as 50.2. And in green, I have here, would be done on exam, okay? So I just kind of reminded you. For homework, go ahead and give it a try, however you want to do it. Feel free to butcher it. I've definitely butchered my fair share of math problems. But ultimately get to a value for x, and then plug, like we've been doing, x back in here to get your equilibrium concentrations. Okay? All right. Next one. In this one, you have to, okay, and this one, My hint is you must, well, it's not finishing that thought. It's like frozen. This I know that it's gone into some other word. If you have a little bit of everything, it's not obvious where it's going to go. It could be a decomposition. It could be, you know, an exchange equilibrium. I guess it could be. But just anything that's in equilibrium, if you have a little bit of everything, you're like, I don't know which way it's going to go. Does that make sense?
Kind of, but then how do you know even if you don't have a little bit of everything?
Oh, okay. Well, say you were limping along, and in this case, let's just say we had some of the product and some of the reactant. And we didn't have any of the other product. I'm trying to think, but to me, just intuitively, you can't have zero, and to me, it's gonna have to go that way. I would have to double check. I'll try to ask Carl if that kind of makes sense to him too. But does that make sense to you too?
Kind of, like, I get it as far as, like, concept where I'd be able to do it on a test, but actually, like, understanding the full reason why.
When in doubt, knock out a QC and compare it, and see what you come up with. You can't go wrong coming up with the reaction quotient, right? But
But just for the purpose of these problems, if you have a little bit of everything, you know that you're gonna need to.
mhm. And I guess in that case, if I was on a test, because you could tell I'm unsure about if it's really that obvious. If I was on a test, we had some COBR2 and some CO, I would probably knock out a QC and compare my reaction quotient with my KC to see which direction I needed to go. That just seems weird that you wouldn't go that way. I guess one way is, if it wasn't at equilibrium, you'd have to go that way because you couldn't proceed back the other way because you didn't have both products. You know, so if it wasn't at equilibrium, it's going to have to go to form some of that other product.
Okay, yeah, that makes sense.
Yeah. So this one, my hint was you need to make sure you get to molarities from the moles and volume. You guys should be fine there. They're little red boxes, red circles. You'll get to, those will be real numbers because you're given initial concentrations here. In this case, let's see if we were just talking about this. Yeah, so in this case, it says you start with SbCl3. If you're like me, I hate it when these look like Greek to me. So you have SbCl3, okay, and 0.160 moles of Cl2. So you have both of the products, but none of the reactants. So just as we were talking about, these will be negative X and that will be positive X. You don't have to do. And then it's kind of like the other ones, I think. So for this one, DRAT, you have to go clear from grams to moles and then divide by the volume to get molarities. Okay, and I'm trying to emphasize because on the test, for some reason, a lot of times, I'll say students, sometimes I say we, but students tend to want to just go with grams, and you can't go with grams in these expressions. So here's kind of what the ice chart would look like. We have 2 reactants and 2 products. Notice that we don't have any of the CO2. And, but this is actually an example of like what, notice I went ahead and said, even though we have, of these 4 things, we have 3 of them, I'm like, dude, the one that you don't have any of, it's going to have to go that way. So that's why I had these as plus, and the stoichiometry is all 1. So, same as previous. Let's see, get initial molarities. Oh, this is one now, question number 38. You do have to come up with a QC and compare your reaction quotient to your KC to know which direction it's going to go. And it kind of switches it up a little bit. We don't have ones across the board with regard to stoichiometry. So you're going to have some kind of, you know, interesting things going on with regard to your change. So this is like the second problem we did. So I went ahead and have an ice table here. Notice I can't say whether it's X or plus X or minus X because you're going to have to figure that out. Okay? All right. And then you should be able to solve for X because you're given KC, and then plug that back into down at the bottom. So this 39 is very similar to 38. So then you have to do the QC, right, QC. All right. Oh, there's one more. Oh my gosh. No, there wasn't. Okay. It's just a blank page. All right. So I'll push those out there and have a good weekend.
Thank you.
Happy Easter.